All right, here's another accumulation problem. Notice this one, we're given a table. So we've dealt with trig functions, we've dealt with trig functions and piecewise functions. Now we're looking at a scenario where they've given us a table, and it's nice. They've actually given you a little bit of an illustration to kind of help you visualize what's going on in this situation. So let's jump in. Part A says use a midpoint Riemann sum with 3 subintervals of equal length to approximate the total amount of water that was pumped into the pool during the time interval 0 to 12 hours. Show the computation. So you got to show the work. And notice they're always going to set it up perfectly, okay? They said 3 subintervals of equal length. So here's one subinterval, that's length 4. Here's another one, that's length 4. Here's another one, that's length 4. And they want midpoint. So you're going to be using the numbers that are in the middle. So midpoint, remember, just goes back to the rectangles. Now, it can't hurt to show kind of the idea of what we're talking about here. We're going from 0 to 12 of that function. They name that one P of t. P of t dt is equal to, we're just talking rectangles here. So the width of each one is 4, so I'm just going to keep that in front. The height, we've got 46, 57, and 62. Now, the good thing is, if you're doing this is calculator active. Type it in, okay? Type it in. Don't try and do those computations by hand. I know they're not that difficult, but don't risk messing them up. You get 1 point for that setup there, showing the 4 times the 46, 4 times 57, and 4 times 62, and you get 1 point for your answer. Okay, part B. So that was easy. 2 points, 2 out of 9, not too bad of a start here. Part B, calculate the total amount of water that leaked out of the pool during the time interval 0 to 12. So another function. Water is leaking from the pool according to this function right here. So total amount that leaked, we're just talking 0 to 12 of R of t. Again, get in the habit of just writing the function there. Don't worry about copying it down, and then just put it directly into your calculator. And you get 225.594, and that's, of course, cubic feet. You get 1 point for the integral, you get 1 point for the answer. So you got to write that down. Even though this is calculator active and you probably know exactly what you're doing, you have to write down the setup. Always, always, always write down the setup, especially if you're just putting something straight into the calculator. Don't skip the setup step. So far, so good, right? That's, if you just remember, total amounts, okay? Total amounts, it's always accumulations, integrals. It's right there. You got half the points. You've got almost half the points already, 4 out of 9. Part C, use the results from parts A and B to approximate the volume of water in the pool at time 12 hours. Well, hello. Let's see here. What does it say? We start with, and this is what most people are going to forget. Most people are just going to take, we pumped in 660, we leaked 225. Most people are going to forget this initial condition. It started with 1,000 cubic feet. It started with 1,000 cubic feet. So we start with 1,000. We add what we pumped in, and again, here's another example of where you should show your setup, and we subtract what leaked out. And that ends up giving us 1,434.406. And it says round to the nearest cubic foot, so please, please, please follow the instructions there. So again, it never hurts to write this in words. At time t equals 12 hours, the volume of water in the pool is approximately 1,434 cubic feet. Okay, so again, don't overlook those initial conditions. If they give you an initial condition and you never use it anywhere in the problem, warning lights should be going off. So that's only 1 point. So even though it took some work there, it's telling you to use A and B. And then here's another good example. If you didn't really know how to get A, which hopefully you do, and B, if you don't know how to get those answers, if you run across a problem like part C that asks you to use A and B, then just go back up to A, write down a reasonable number, go up to B, write down a reasonable number, and then use those two numbers in your calculation for part C. And you'll have a really good chance of still being able to get that point for part C, even though you didn't get the points for A and B. Or maybe you didn't get the full points for A and B. All right, part D. Part D, it says find the rate at which the volume of water in the pool is increasing at time t equals 8 hours. Find the rate at which the volume of the water in the pool is increasing at time 8 hours. So they gave us the volume formula for a reason. Volume equals pi r squared h. Guess what this is? A related rates problem. So we've got dV over dt equals, remember, keep that pi out front. No point in dealing with that. You've already got a product rule to deal with. So first times the derivative of the second plus derivative of the first times the second. Now let's think about what's constant here. Is the radius of this pool here changing? Okay, it's not. It's the shape of a cylinder. It always has a radius of 12 feet. It always has a radius of 12 feet. So dr over dt is 0. Okay, dr over dt is 0. Okay, so let's plug in what we know. dV over dt. Do we know the change in the volume? No, that's what we're looking for. The radius is always 12. The change in the height. Ooh, we don't know that either. That's what they're asking us in the second part of the question. How fast is the water level in the pool rising? Okay, so we got another unknown. And then that whole part was 0. So we don't need that. I mean, multiplying by 0 over there, that's gone. All right. So apparently I'm solving the wrong part of the problem right here. But that's okay. It happens. All right. So the second part of this question is asking for how fast is the water level rising. So that's dH over dt. So it must mean that I should be able to figure out dV over dt in another way. So let's think about this. The volume is changing. It's being pumped in and it's leaking out. So wouldn't it make sense that the rate at which the volume is changing, V prime of t, would be equal to the pumping in minus the leaking, right? The volume is changing according to what's being pumped in minus what's leaking. So we're asking specifically at time 8. So P of 8 minus R of 8. P of 8 comes from the table. P of 8 is 60. R of 8 comes from the calculator. 25e to the negative 0.4. So that ends up giving 43.241 is V prime of 8. And we're going to turn around, so you get 1 point for that. You get 1 point for this equation right here, your related rate equation. Then we need to plug in, because it's asking for at that same time, so we plug in that rate of change for the volume. And then we just need to divide both sides by 144 pi. Very carefully in our calculator, making sure we put parentheses around the 144 pi. And so we get that dH over dt is equal to 0.095. And let's think about our units here because it does say indicate units of measure in both answers. So let's go back to the volume and fix that. Volume is going to be cubic feet per, what does it say? Per hour is what all of our other rates are in. And so then this is talking about the height. So the height's going to be in feet per hour. And so you get a point for v prime of 8, you get a point for dv over dt, what that's equal to, you get a point for this answer, and then you get 1 point for your units on both. You got to have both units right to get that point right there. Okay, so anytime they say include units, you can about guarantee somewhere in the problem you're going to get a point for units. So you want to make sure that you include those anywhere that it's applicable.